All right, so here's our next problem. Uh, Looks a little bit similar, y double dot plus 6y dot, but now we've changed it from, I think the last one was 9y to now 18y. Okay, we're still not going to have an input, so the same initial conditions. But for this one, so this is now a little bit different here. So we've done one with two real roots. We did one with repeated roots. Now we're having complex roots. One of the complications that comes from second order as you go to higher order systems. So you can have complex roots. Okay, well, that is what we indeed have here. Okay, uh, so let's start to analyze this a little bit. So from everything we've seen thus far, we can look at this minus 3, the real part. So if we flip that, the time constant is 1/3, the settling time is 4/3 of a second. Okay. And this would be the complementary solution. C1 e to this complex number t, and C2, this would be the conjugate. Okay. And when you have complex numbers, everything appears in conjugates. All right. So we can then break this down. Here what we have. So we have minus 3's are common here. So we have an e to the minus 3t and then 3it and e to minus 3it. So we need to contemplate what is this e to the 3it. And hopefully you've had this in your math course. If you haven't, you're going to get it now. We're going to use Euler's identity, and that explains what e to the 3t is. So if you have an I, okay, and I have the I, really probably should have it as I3t, would make more sense, because the 3t, not the I, are going to represent cosine 3t plus, then the I goes here, sine 3t. Okay? So if I had e to the I theta here, instead of 3t, it would be cosine theta plus I sine theta. All right? And you'll notice if you square these, you get cosine squared plus sine squared equals 1. So what you're really doing here is in a complex plane, the unit circle, and you're just kind of going around the circle. Okay? So if you had, here's the real axis, here would be the imaginary. So you're kind of doing this sort of action. Okay. Now, because you have the real and the imaginary, you're going around in the circle. But if you break this down into just the real part, you have oscillation back and forth. Okay. So, what can we do with e to the minus 3it? So if you have a minus sign in there, a cosine of minus theta is just simply cosine theta, but the sine of minus theta is minus the sine of theta. So this minus sign comes out here. So e to the minus 3it is cosine 3t minus I sine 3t. All right. And if you play with this, here's this one, and here's that one, you can add them together in interesting ways. If e to the 3it plus minus e to the 3it divided by 2 basically cancels out the complex portion, you get cosine 3t. If you have e to the 3it minus, instead of the plus, minus 3it divided by 2I, you get sine of 3t. So you can use this to form sinusoids. All right. So here's our complementary solution. C1, e to the minus 3 plus 3it plus C2, e to the minus 3 minus 3it. Okay? So we would solve this in the same way. Y0 equals 2. Plug zeros in here for t. You're just going to get C1 plus C2. And we can solve for C1. Okay? And then we have our next term down here. This isn't showing up so good. Yeah, that's better. Equals 4. So here's y dot of 0 is 4. So you take the derivative of our terms up here, which is easily done. Make that a little easier to see. And now we we would substitute in for C1, 2 minus C2. Now we have one equation. And multiply everything out. We have 10 minus 6i equals minus 6i C2. All right. So if you solve for C2, you get C2 equals 1 plus 10 over 6i. And what's nice is when you do these problems, everything has to be in complex conjugates. If not, when you go to get a response, the response won't be real. You need to have these things cancel out. All right, so the second you compute C2, you don't need to think about it. You can write C1 equals this. You know it has to be that way. Okay, and so now here's our response. Y, the initial condition response is e to the minus 3t. We have this 1 minus 10/6 over I, e to the 3it, and 1 plus 10 over 6i, e to the 3it. But here's the problem. You go up here and you look at this. Here's the differential equation, and we have real initial conditions. So you know the response is real. So you have all these i's. You know if you could reduce this thing down, it would just be a solution that's real. You could get rid of these complex numbers. That's the thing we need to look at next. So here's the problem we had. Here's our initial conditions. Initial condition response. Okay. And so we want to simplify this down. All right. So this, anytime you see a complex number, a plus bi, it can be written as a magnitude times ei theta. So this is magnitude, that's sort of direction. Okay. Think of it as, so this is a vector. So this, you can express a vector in the complex plane this way or that way. All right. So what we want to do is express this in this form. And if we did that, that'll be an ei theta. And then here we have the ei other stuff. Maybe we can simplify it down. Let's see what happens. Well, so we have, these both have the same magnitude. So 1 squared plus 10 over 6 squared, square root, is 1.94. All right. Then we have, so we can compute our phase. So 10 over 6, if we use this one over here, this is the y, that's the x. So we'd have inverse tangent of 10 over 6 on 1 is 1.03 radians. Well, that means the other one is minus 1.03 radians. So we got that. And so here's what happens. So we now have, this is 1.94 and 1.03 radians. So we can express that. Here's 1.94 and e minus 1.03 I. Okay, then the other one is positive 1.03 I. So now how can we reduce this some more? Well, we can bring these all together. So I have a 3t I minus 1.03, and here's a minus I, 3t minus 1.03. Okay, so these are conjugates. That works. Well, notice what we have then. 1.94, these factor out. E to the minus 3t, we can keep that out. And this, we have a positive sign here. We had this positive sign right there. So that looks like a cosine. E to the it plus another e to the minus it divided by 2. So this piece, go check the identities we had. Let's bring this right up here. E to the 3, notice here we have e to the 3it plus e to the minus 3it divided by 2. That's cosine 3t. Okay, so instead of 3t here, we have 3t minus 1.03. All right, so that's the piece. So we have e to the I this plus e to the minus I, the same thing. So now we have 2 cosine 3t minus 1.03. You need to follow this. Take some time, study what's happening here. All right? This is very important. All right? Well, now we have that. We can simply take this 2, bring that out here. We have 3.88 e to the minus 3t and a cosine. Right? A much easier way of writing this than not dealing with all those i's. So what's the bottom line of this? we're looking at initial condition response where we had complex roots. So we could have done it the way we did it with putting the root minus 3 plus or minus 3i as an exponent. Or what we found from doing this problem is when you have complex roots, rather than going e to the complex number up here, we can simply take the sum. It's going to be some magnitude a, e to the minus 3t. This will be whatever the real part is. Cosine, here's the imaginary part, plus theta. Or we could have done a e to the minus 3t sine of 3t plus theta. And now we have to solve for these two constants as opposed to, let's see, bring this over here. So here's the alternative. Here is the complementary solution we started from, C1, e to the minus 3 plus 3i versus C2, e to the minus 3 minus 3it. Putting the roots there. Or we could choose to use either one of these. And now our two constants become this magnitude and that phase. Both work. That's our choices. Anyway, this fun stuff here. Obviously, a lot of intense algebra. The good news is we're going to be able to do this far more simply later. But this is how we do these. And so we're just reviewing what you've had in your differential equations course. So this should all be very accessible. And that's all for this video. I'll see you again soon.